Hello there. Welcome to the Science Owl Station channel. Today we begin a gentle journey into one of the quietest, strangest ideas the universe has ever offered us. Black holes and the slow way they bend time itself. Imagine yourself floating far from Earth, not moving, not falling, simply resting as the stars drift like distant lanterns. Space is calm here. There is no urgency, no sound, only the soft suggestion of motion, as if the universe itself has decided to speak more slowly tonight. So, before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. And if you feel like it, let me know in the comments where you're listening from and what time of day or night this finds you. Some of you may be lying in bed, others driving through darkness, others just letting the day dissolve. Wherever you are, let that be enough. Now, allow your attention to soften as we begin. A black hole, despite its name, is not really a hole at all. There is no empty tunnel punched through space. There is no opening waiting to swallow the universe. Instead, a black hole is a region where space and time themselves have been gently, relentlessly curved. Mass presses so deeply into space-time that the fabric yields, folding inward, like a heavy stone resting on a calm sheet. Nothing mystical about the process, just gravity taken to its quiet extreme. Because space and time are woven together, bending one means bending the other. Near a black hole, time does not behave the way it does here on Earth. Seconds stretch, moments loosen. The closer you drift, the slower time flows for you compared to the rest of the universe. In theory, you could hover near a massive black hole and watch distant galaxies age, collide, and fade while only a short while passes for you. One long, peaceful nap could outlast the entire span of human civilization. At the boundary of a black hole lies something called the event horizon. This is not a surface you can touch, and it does not announce itself with light or sound. It is simply a point of no return, a place where the curvature of space-time becomes so steep that all possible paths forward lead inward. Crossing it feels like nothing at all. No jolt, no sudden darkness, no warning. From your own perspective, the universe remains calm and continuous. From far away, however, the story looks different. To a distant observer, anything falling toward a black hole appears to slow down, dim, and freeze near the event horizon. Time itself seems to stall. This is not because the object stops, but because its clock is running more slowly compared to the outside universe. The black hole does not rush. It waits, patiently. Despite their reputation, most black holes are remarkably quiet. Supermassive black holes, the kind that sit at the centers of galaxies, often spend billions of years doing almost nothing at all. They are not constantly feeding or tearing stars apart. They simply exist, holding their place, anchoring the slow rotation of stars and gas around them. In this sense, they are less like monsters and more like deep sleepers. At the heart of our own Milky Way galaxy lies such a sleeper, Sagittarius A*, a black hole with a mass about 4 million times that of our Sun, sits calmly at the center, influencing the orbits of nearby stars without drama. Those stars circle it gracefully, following predictable paths, as if obeying a cosmic lullaby. The universe may also contain black holes of a very different kind, primordial black holes. These hypothetical objects could have formed in the earliest moments after the Big Bang, when space itself was dense and uneven. Some of them may be incredibly small, perhaps no larger than a grain of dust, yet enormously massive. If they exist, they drift silently through space, unnoticed, like leftover dreams from the universe's infancy. What makes black holes especially gentle in a strange way is that they do not actively pull things in like cosmic vacuum cleaners. They do not reach out. They simply curve spacetime, and objects follow the paths that curvature creates. If the sun were magically replaced by a black hole of equal mass, Earth would continue orbiting exactly as it does now, though the sky would grow very dark. Black holes teach us that the universe does not always communicate through violence. Sometimes it whispers through patience, through stillness, through time stretched so thin it nearly stops. They remind us that endings are rarely abrupt, and that even the most extreme places in reality follow quiet rules. As you listen, notice your breathing, the gentle rhythm of it, in and out, like orbits, like tides, like the slow turning of galaxies around invisible centers. There is no need to hold on to every detail. These ideas are meant to drift past you, to be felt more than remembered. Black holes are not interruptions in the universe. They are part of its long, unhurried story, a story told not in explosions but in curvature, not in noise but in time. Wherever you are, let the world slow down for a while. Soften your gaze, let the hum of life around you fade, and gently drift with us into tonight's quiet exploration. The universe has many ways of falling asleep, and some of them begin with stars far larger than anything we can truly imagine. Long before a black hole ever exists, there is usually a star bright, massive, and burning steadily for millions of years. These stars live their lives balancing two quiet forces: gravity pulling inward and nuclear fire pushing outward. For most of their existence, those forces rest in harmony, like a slow, even breath. But not every star is destined for a gentle fading. Only the most massive ones carry enough weight to bend spacetime into something deeper. A star must be at least 3 times the mass of our sun before it can even consider becoming a black hole. Anything smaller ends its life differently, settling into calmer states. Size in the universe decides destiny. When a massive star runs out of fuel, its internal fire weakens. Gravity, patient and tireless, finally takes over. The core collapses inward, and the outer layers rebound in a tremendous release of energy known as a supernova. Despite the violence of the explosion, what remains afterward is not chaos, but stillness. At the center, matter compresses beyond familiar limits, falling inward until space itself yields. Most black holes we know began this way as stellar remnants. They are not born screaming. They emerge quietly from collapse, carrying the memory of a star that once shone. In this sense, a black hole is less a destroyer and more a monument, a record of a star that lived intensely and then let go. Before a black hole forms, a star may pass through an intermediate state, becoming a neutron star or a pulsar. Neutron stars are incredibly dense, packing more mass than the sun into a sphere only a few kilometers wide. Pulsars, a special kind of neutron star, rotate rapidly and send out precise beams of radiation, like slow cosmic lighthouses sweeping through darkness. They are often described as the last visible heartbeat before deeper sleep. If even a neutron star cannot resist gravity, collapse continues. There is no sudden moment where the universe announces what is happening. No clear dividing line. Matter simply keeps falling inward, compressing further, until spacetime curves so steeply that an event horizon forms. From the outside, the transformation looks slow and unfinished. From the inside, it simply happens. Stellar black holes can spin, sometimes incredibly fast. As the original star collapsed, it conserved its angular momentum, much like an ice skater pulling in their arms to spin faster. Yet despite this rotation, the event horizon itself appears calm. There are no waves on its surface, no visible turbulence. Motion hides beneath perfect stillness. Some stellar black holes are not alone. In binary systems, they orbit companion stars, locked in long gravitational dances. Over time, gas from the companion star may drift toward the black hole, forming a glowing accretion disk. This process can be slow and subtle, unfolding over thousands or millions of years. The black hole feeds not with urgency, but with quiet inevitability. To an outside observer, this feeding is one of the few ways a black hole announces its presence. X-rays and faint glows emerge as matter heats up before crossing the event horizon. Then, just as softly, that matter disappears from view, becoming part of the black hole's mass. Nothing dramatic remains, only a slightly deeper curve in spacetime. What is remarkable is how ordinary these processes are, at least by cosmic standards. There is no malice, no intention, no hunger. Gravity simply follows its rules. Stars age, balance fades, collapse continues. The universe does not rush any of it. As you listen, imagine a massive star near the end of its life. Not exploding yet, just slowing. Its nuclear reactions weakening, its light growing subtly less intense. There is no sadness in this image, only completion. The star has done its work. It has forged elements, warmed space, shaped worlds. Now it rests. Black holes formed this way are not anomalies. They are part of the natural rhythm of stellar life cycles. Birth, balance, collapse, rest. Even the deepest darkness begins with light. And perhaps that is why black holes feel strangely calming when viewed this way. They are not interruptions. They are continuations. The universe learning how to be still after burning so brightly for so long. Let these thoughts drift without effort. You don't need to hold on to them. Like starlight traveling across space, they arrive when they're ready and fade when it's time. At the very centers of galaxies, far from the quiet endings of individual stars, something much larger rests. Almost every large galaxy we have studied appears to be organized around a single, immense presence, a supermassive black hole. These are not objects formed from one collapsing star, but from long histories of growth, mergers, and slow accumulation. They sit at the heart of swirling star systems like deep anchors, holding the slow architecture of galaxies together. Our own galaxy is no exception. At the center of the Milky Way, hidden behind clouds of dust and gas, lies Sagittarius A star. It is enormous by any human measure, weighing about 4 million times as much as our Sun. Yet it behaves with surprising restraint. It does not blaze or roar. It emits no constant glare. Instead, it rests quietly, influencing its surroundings through gravity alone. For decades, astronomers tracked the motion of stars near the galactic center, watching them trace elegant, looping orbits around an unseen mass. These stars move quickly, some completing their paths in just a few years, yet their motion is smooth and predictable. There is no chaos here, only obedience to gravity's gentle geometry. From these calm orbits, the presence of Sagittarius A** was inferred long before it was ever imaged. Supermassive black holes like this spend most of their lives in a dormant state. They are not always feeding. They are not always active. For long stretches of cosmic time, they simply exist, quietly bending spacetime while stars drift past in slow, luminous arcs. In these periods, galaxies appear calm and balanced, their central black holes barely noticeable. But occasionally, circumstances change. Gas clouds wander too close. Stars stray inward. When enough material begins to fall toward a supermassive black hole, it can awaken. The accretion disk brightens. Radiation pours outward. The galaxy's center becomes one of the most luminous regions in the universe. In this active phase, the black hole is called a quasar. Quasars are so bright they can outshine the combined light of hundreds of billions of stars. And yet, even then, the black hole itself remains unseen. All that brilliance comes from matter spiraling around it, heating up, colliding, and releasing energy before crossing the event horizon. The black hole remains silent at the center of the storm. Not all supermassive black holes stay in one place forever. When galaxies collide, a slow, graceful process that can take billions of years, their central black holes may eventually find each other. They spiral inward, orbiting in widening arcs of gravity, until they merge into a single, larger presence. The galaxy reshapes itself around this new center, settling into another long era of calm. Some black holes, however, may not end up at the center of anything at all. There is evidence suggesting that certain black holes wander through intergalactic space, expelled during past mergers or formed in isolated regions. These nomadic black holes drift alone, without stars or galaxies to mark their passage. They are almost impossible to detect, and they move in silence between the great structures of the universe. Despite their size, supermassive black holes do not dominate galaxies through violence. They do not tear stars apart indiscriminately. They influence structure through patience. Their gravity guides motion gently, shaping orbits and stabilizing flows of gas over immense timescales. In many ways, they act more like steady hearts than ravenous mouths. It is easy to imagine the centers of galaxies as turbulent, chaotic places. But in reality, much of the time, they are serene. Stars move in calm paths. Gas drifts slowly. The central black hole rests, neither growing nor shrinking in any dramatic way. The galaxy breathes around it. As you picture this, imagine standing far above a spiral galaxy, watching it turn slowly in the dark. Arms of stars curve outward like soft brushstrokes. At the center, unseen but essential, something holds it all together. Not through force, but through quiet presence. Supermassive black holes remind us that size does not require aggression, that immense influence can exist without constant action, that sometimes the most powerful thing in a system is the one that moves the least. Let this image settle. A galaxy turning, a center at rest, time stretching wide and unhurried. When we talk about black holes bending time, we are really talking about how reality itself becomes flexible near extreme gravity. Far from any massive object, time moves at a steady, familiar pace. Seconds follow seconds, cause follows effect. But as gravity deepens, Time begins to loosen, like a dream that no longer obeys ordinary sequence. Near a black hole, this effect becomes profound. The closer you drift toward it, the more slowly your time flows compared to the rest of the universe. From your own perspective, nothing feels strange. Your thoughts remain clear, your breathing stays steady, but far away, clocks tick faster and faster. Entire eras unfold while your own moments stretch gently apart. If you could hover near a black hole and look outward, the universe beyond would appear to speed up. Stars would flare and fade. Galaxies would evolve. Civilizations could rise and disappear in what feels, to you, like a brief passing of hours. Time, usually so rigid, reveals itself as something soft and relative. This is not an illusion. It is a direct consequence of spacetime curvature, predicted by Einstein's theory of general relativity and confirmed by careful observation. Gravity does not simply pull on objects. It reshapes the stage on which time and space perform. Near a black hole, that stage tilts steeply inward. As something falls toward a black hole, another strange effect unfolds. Tidal forces stretch it gently at first, then more strongly, pulling different parts at different rates. This process has been given a whimsical name, spaghettification, because objects are drawn out into long, thin shapes. Despite the playful term, the effect itself is quiet and inevitable, not sudden or violent. Light, too, bends under these conditions. Photons passing near a black hole follow curved paths, creating gravitational lensing. Distant stars appear duplicated, smeared into arcs, or arranged in luminous rings. These distortions are not tricks of perception. They are maps of curved spacetime made visible. Sometimes, this bending allows us to see objects that would otherwise be hidden. Light from behind a black hole can be wrapped around it, reaching us along unexpected routes. The universe reveals itself indirectly through detours shaped by gravity. Inside a black hole, our usual understanding of time may no longer apply at all. The familiar distinction between past and future becomes uncertain. Some theories suggest that time itself points inward, making movement toward the center unavoidable. In such a place, before and after may lose their meaning, dissolving into something more abstract. From far away, however, nothing ever seems to cross the event horizon. Matter slows, reddens, fades. Its image freezes at the boundary, growing dimmer until it blends into darkness. The black hole appears to grow without ever visibly consuming anything. What falls in is never seen to arrive. This contrast between what is experienced locally and what is observed from afar is one of the quiet wonders of black holes. Two equally valid descriptions of reality exist at once, depending on where you stand. Neither is wrong. They simply belong to different frames of time. As you rest with these ideas, there is no need to untangle every detail. Let them remain soft around the edges. Like dreams, they do not need to be precise to be meaningful. What matters is the feeling they carry, that time is not rigid, that reality is more flexible than it appears. Black holes do not break the universe. They reveal its deeper structure. They show us that time can stretch, that light can curve, and that certainty fades at the edges of extreme gravity. Let these thoughts drift past you, slow and unforced. Like starlight bent on its way to you, they have taken a long path to arrive. Darkness in the universe is rarely absolute. Even around black holes, objects famous for swallowing light, there is often a gentle glow. This light does not come from the black hole itself, but from the quiet activity surrounding it. Before anything disappears into darkness, it usually shines. Contrary to popular imagination, black holes do not pull matter inward like cosmic vacuum cleaners. They do not reach out or grab. Instead, they reshape spacetime so deeply that nearby matter naturally follows curved paths inward. Objects fall not because they are chased, but because the geometry of space guides them there. Gravity here is not forceful. It is persuasive. As gas and dust drift toward a black hole, they rarely fall straight in. Instead, they begin to circle, forming what is known as an accretion disk. Within this disk, particles move at tremendous speeds, brushing past one another, colliding softly, transferring energy through friction. Over time, this motion heats the disk to extraordinary temperatures, sometimes millions of degrees. At these temperatures, matter begins to glow, first faintly, then intensely. Visible light gives way to ultraviolet radiation and then to X-rays. From far away, this glow is often the only clue that a black hole is present at all. The darkness announces itself through light. These emissions are sometimes described as the sounds of a black hole, even though they are silent in space. They are the final expressions of matter before it crosses the event horizon, like a whisper fading at the edge of sleep. Once past that boundary, the glow disappears, and the universe receives no further signal. In some systems, black holes do something even more unexpected. Instead of quietly consuming all incoming material, they expel some of it outward in narrow, focused streams called jets. These jets can stretch thousands, even millions, of light years into space, carving glowing paths through interstellar and intergalactic gas. How jets form is still an active area of study, but they appear to be connected to the black hole's rotation and magnetic fields. Energy is extracted not from the black hole's interior, but from the motion of spacetime around it. In a way, the black hole exhales, even as it continues to draw matter inward. These jets are not chaotic. They are remarkably stable, maintaining their direction across vast distances. Galaxies can bear the marks of past jet activity long after the black hole has returned to dormancy, like faint memories etched into cosmic surroundings. Despite all this activity, the black hole itself remains hidden. Its event horizon emits no light, no radiation, no signal that can be directly observed. All brightness comes from the boundary regions, from matter still outside, still visible, still part of the universe we can measure. And yet, there is one more subtle glow to consider. According to quantum theory, black holes are not completely dark. They emit an incredibly faint radiation, now known as Hawking radiation. This effect arises from quantum fluctuations near the event horizon, where pairs of particles briefly appear and vanish. Over immense spans of time, this radiation allows black holes to lose mass, evaporating slowly. For stellar and supermassive black holes, the process is unimaginably slow, far longer than the current age of the universe. But it means that black holes are not eternal. Even the deepest darkness fades eventually. This idea that black holes can glow however faintly adds a quiet softness to their image. They are not perfect voids. They are participants in the long exchange of energy and time that defines the cosmos. As you listen, imagine a distant black hole, wrapped in a thin, glowing disk, jets stretching faintly into darkness, the whole system breathing slowly across millions of years. Nothing hurried, nothing wasted, just motion easing toward rest. Let the glow dim in your mind. Let the motion slow. There is no need to follow it further tonight. Space is often imagined as silent and still, an empty stage where events unfold without leaving a trace. But when black holes move, space itself remembers. It stretches, compresses, and gently vibrates, carrying those motions outward in slow, fading waves. These vibrations are known as gravitational waves, and they are among the quietest messengers the universe has ever sent. When two black holes begin to orbit each other, the process is unhurried. They circle at great distances at first, tracing wide paths through curved spacetime. With every orbit, a tiny amount of energy is released in the form of gravitational waves. The waves are weak, almost imperceptible, but over millions of years, they slowly carry energy away. The black holes drift closer, their dance tightening, their rhythm quickening. This long approach is not dramatic. There are no flashes of light, no sudden disturbances. From far away, nothing seems to change. Only space-time itself is quietly rippling, like water disturbed by a stone dropped long ago. The universe does not announce these moments. It simply records them. Eventually, the black holes draw so near that their orbits accelerate rapidly. In the final moments, they move at significant fractions of the speed of light. Space-time twists and shudders as the two horizons merge. For a brief instant, more energy is released than by all the stars in the observable universe combined. And yet, no light marks the event. Only a passing wave in the fabric of reality itself. These waves travel outward at the speed of light, crossing galaxies, drifting through clusters, passing silently through planets and people. By the time they reach Earth, they are unimaginably faint. Detecting them requires instruments of extraordinary sensitivity and patience. The Laser Interferometer Gravitational Wave Observatory, known as LIGO, listens for these distant echoes. It does not use sound or light in the traditional sense. Instead, it measures minuscule changes in distance, far smaller than the width of an atom, as space-time stretches and compresses. When a gravitational wave passes through, the instrument notices the universe breathing. The signals LIGO detects are not loud. They are gentle chirps, brief and subtle. But within them lies a story. The masses of the black holes, their spins, the moment they became one. Each detection is a whisper from a past event that occurred millions or billions of years ago. After two black holes merge, the newly formed black hole is not immediately calm. It vibrates. The shape wobbles slightly, settling into a stable form. Physicists call this phase the ring down, because it resembles the fading tone of a bell struck once and left to rest. With each vibration, energy is released as gravitational waves, until the black hole becomes perfectly still again. Then silence returns. These mergers remind us that even in the deepest darkness, motion leaves traces. That space itself is not rigid, but responsive. That the universe keeps memory not in images, but in vibrations that travel patiently across time. As you rest with this idea, imagine those waves passing through you now. Not as force, but as gentle stretching. Nothing to notice, nothing to fear. Just a reminder that you are part of a universe that moves softly, even in its most extreme moments. Black holes collide without sound. Space remembers without effort. And everything, eventually, settles back into quiet. Somewhere in the vast inventory of the universe, records are being kept. Not in books or databases, but in mass, distance, and time. Black holes, quiet as they are, hold many of these records. Extremes of size, extremes of age, extremes of patience. They are the universe's way of reminding us how large and how old reality can be. Among the largest known black holes is one called TON 618. It lives at the center of a distant quasar and carries a mass tens of billions of times greater than our Sun. Numbers like these are difficult to feel. They slip past intuition. One way to imagine it is to think of spacetime itself sinking deeply under such weight, forming a curve so broad that entire solar systems could drift within it without noticing the descent. Despite its immense size, TON 618 does not tear the universe apart. It exists, it shapes, it rests. Even the largest black holes obey the same quiet rules as the smallest ones. Gravity does not change its tone simply because the scale grows larger. At the other end of the spectrum are black holes that may be incredibly small. According to theory, the smallest possible black holes could be no bigger than an atom, yet weigh as much as a mountain. These hypothetical objects would be unimaginably dense, folding mass into a region so tiny that spacetime itself would be sharply curved at microscopic scales. If they exist, they pass unnoticed, leaving no light, no sound, no trail. Spin adds another layer to these records. Some black holes rotate at extraordinary speeds, approaching the ultimate limits set by physics. As they spin, they drag spacetime around with them in a process called frame dragging. Space itself begins to swirl, like water pulled into a slow whirlpool. And yet, from a distance, the black hole still appears calm, its horizon smooth and unbroken. Distance, too, keeps its own quiet statistics. The nearest known candidate black hole lies only about 1,500 light-years from Earth. In cosmic terms, this is nearby, and still it poses no threat. It does not loom or approach. It simply exists in its own stellar neighborhood, invisible and inactive, like countless others scattered throughout the galaxy. Age is perhaps the most humbling record of all. Some black holes formed very early in the universe's history, only a few 100 million years after the Big Bang. These ancient objects have been resting for nearly the entire lifespan of the cosmos. They have watched galaxies form, collide, and fade. They have outlasted stars, planets, and likely entire civilizations. What is striking is not how extreme these records are, but how quietly they are held. There are no plaques, no announcements, no signals marking largest or oldest. These distinctions matter only to observers like us, trying to place ourselves within the scale of things. Black holes do not compete. They do not compare themselves. They simply remain, carrying the weight of their history in the shape of spacetime around them. Their records are written not in numbers, but in curvature. As you listen, allow these scales to soften. You don't need to grasp them fully. It is enough to sense that the universe is spacious beyond urgency, old beyond memory, and patient beyond measure. Records, after all, do not need to be read all at once. They can rest just like you. Not all questions about black holes are meant to be answered quickly. Some of them linger, drifting at the edges of understanding, inviting speculation rather than resolution. These are the questions that turn black holes from objects into ideas, places where physics softens into philosophy and certainty gives way to quiet curiosity. One such idea is that a black hole might be more than an ending. Some theories suggest it could be a kind of doorway, a bridge to another region of spacetime, or even another universe entirely. These ideas are not claims, only possibilities whispered by equations. If such passages exist, they are likely unstable, fleeting, and unreachable. Still, the thought remains that collapse might also be a form of continuation. Closely tied to this is the black hole information paradox. According to the rules of quantum physics, information cannot be destroyed. But when matter falls into a black hole, it seems to vanish from the universe we can observe. The question becomes gentle and persistent. Where does that information go? Some theories suggest it is encoded on the event horizon itself, stored in subtle patterns too delicate for us to measure directly. Another idea involves wormholes, hypothetical tunnels through spacetime that could connect distant regions of the universe. In theory, black holes might be linked to such structures. In practice, most wormholes would collapse instantly, closing before anything could pass through. They remain mathematical dreams, fragile and short-lived, like thoughts that fade before fully forming. There are also models suggesting that the interior of a black hole could resemble a tiny universe of its own. In these ideas, the singularity is not a point of infinite density, but a compressed region where spacetime folds inward on itself, perhaps giving rise to new expansion elsewhere. These concepts stretch imagination gently, without insisting on belief. One of the most intriguing frameworks to emerge from black hole research is the holographic principle. It proposes that all the information contained within a volume of space can be described by data on its boundary. In the case of a black hole, this means that everything inside might be encoded on the two-dimensional surface of its event horizon. Reality, in this view, behaves less like a solid object and more like a projection. None of these ideas are settled. They are not answers, but invitations, ways of thinking that help physicists test the limits of what we know. Black holes, in this sense, are not puzzles to be solved, but mirrors reflecting the edges of our understanding. As you rest with these thoughts, there is no need to decide what is true. Let the possibilities remain open, like stars seen through thin cloud, clear enough to notice, soft enough to drift. The universe does not rush us toward conclusions. It allows questions to remain, gently unresolved, resting in the quiet space between what is known and what is not. Black holes are often imagined as permanent features of the universe, eternal sinks from which nothing ever returns. But even these deep wells of gravity are not immune to time. Very slowly, almost imperceptibly, black holes fade. Their endings are not sudden or violent. They are among the longest, quietest goodbyes the cosmos knows. In the 1970s, physicist Stephen Hawking discovered something unexpected. When quantum mechanics is applied near the edge of a black hole, the event horizon is no longer perfectly dark. Tiny fluctuations in energy allow pairs of particles to appear briefly, then vanish. Occasionally, one particle escapes while the other falls inward. To a distant observer, this looks like the black hole is emitting radiation. This phenomenon, now called Hawking radiation, is extremely weak. For large black holes, it is far fainter than the cosmic background glow that fills space. but it carries an important implication. Black holes lose mass. They evaporate grain by grain over timescales so vast they challenge comprehension. A black hole with the mass of our sun would take around 10 to the power of 67 years to fully evaporate. That is a number with more zeros than the current age of the universe has seconds. For comparison, the universe itself is only about 13 billion years old. Black holes, then, are not just long-lived. They are patient beyond imagination. Smaller black holes fade more quickly. As a black hole loses mass, its temperature rises, increasing the rate at which it emits radiation. This creates a slow acceleration toward the end. For hypothetical tiny primordial black holes, this final phase could be dramatic, a brief burst of energy released after eons of near silence. Yet even this ending is gentle in context. There is no collapse, no implosion, just a gradual thinning, a quiet release of energy, and then absence. A black hole does not leave behind debris or fragments. It simply stops being. This slow disappearance deepens one of physics' most persistent questions. If information cannot be destroyed, what happens to the information that once fell into a black hole when the black hole itself is gone? Does it escape encoded in Hawking radiation? Is it preserved in subtle correlations? Or does it change form entirely? There is no clear answer yet. What matters, perhaps, is that black holes remind us that permanence is rare in the universe. Even the darkest, densest objects are temporary arrangements of energy and spacetime. As you listen, imagine a black hole far in the future, long after stars have burned out and galaxies have faded. It sits alone in a cold, expanding universe, releasing its final warmth into the void. Nothing witnesses the moment it disappears. No boundary marks the transition. The universe simply becomes slightly quieter. Endings, like beginnings, do not need an audience. Long before stars formed, before galaxies settled into graceful spirals, the universe was a very different place. It was dense, hot, and restless. Space itself expanded rapidly, smoothing some regions while leaving others slightly uneven. In those earliest moments, gravity may have found opportunities to act in unexpected ways. One idea suggests that black holes could have formed almost immediately after the Big Bang. These are known as primordial black holes. Unlike stellar black holes, they were not born from collapsing stars. Instead, they may have emerged from tiny fluctuations in the density of the early universe, where matter briefly gathered just enough to collapse under its own gravity. If primordial black holes exist, they could come in a wide range of sizes. Some might be incredibly small, while others could be much larger, depending on the conditions of their formation. Many would have evaporated long ago through Hawking radiation, but some, especially the larger ones, could still be drifting quietly through space today. Because they emit little to no light and interact almost entirely through gravity, primordial black holes have been proposed as possible contributors to dark matter. Dark matter makes up most of the universe's mass, yet it neither shines nor absorbs light. It shapes galaxies silently. In that sense, it shares a certain calm kinship with black holes. Whether primordial black holes account for any significant portion of dark matter remains uncertain. Observations continue, slowly narrowing the possibilities. As with many ideas in cosmology, patience is required. The universe reveals its secrets gradually, if at all. Another enduring mystery concerns how supermassive black holes grew so large so quickly. Some appear to have reached enormous sizes when the universe was less than 1 billion years old. This challenges simple explanations. Did they begin as unusually massive seeds? Did they grow by feeding continuously? Or did early conditions allow gravity to work more efficiently than it does today? Black holes also stand as some of the strongest evidence for Einstein's theory of general relativity. Their behavior matches its predictions with remarkable precision. And yet, they also highlight where the theory may be incomplete. At their cores, where density becomes extreme, general relativity and quantum mechanics no longer agree. Black holes sit at the boundary between what we understand and what we do not. Looking far ahead, black holes may dominate the universe's distant future. As stars exhaust their fuel and galaxies drift apart, black holes could become the last massive structures remaining. One by one, over inconceivably long timescales, they too would evaporate, leaving behind a universe that is dark, cold, and thinly spread. This possible ending is sometimes called the heat death of the universe. Not a collapse, but a quiet fading. Energy disperses, motion slows, differences flatten out, and eventually nothing much happens at all. As you rest with this vision, there is no need to feel heaviness. The universe is not mourning its future. It simply follows its rhythms, expanding, cooling, and resting in its own time. Black holes, born in chaos, growing in patience, and fading in silence, trace that rhythm beautifully. Black holes do not live only in equations and observatories. They have also drifted into our stories, our films, and our shared imagination. When something cannot be seen directly, the mind naturally fills the space with images. And black holes have become quiet screens onto which human curiosity projects wonder, fear, and possibility. In popular culture, black holes are often portrayed as violent cosmic mouths, endlessly pulling in stars, planets, and entire galaxies. They appear sudden, destructive, and unstoppable. Yet this image is more dramatic than accurate. In reality, most black holes are stable and inactive, influencing their surroundings gently, without spectacle. The contrast between myth and reality says more about us than about the universe. Cinema, in particular, has been drawn to black holes as symbols of mystery. They represent places where normal rules no longer apply, where time bends and certainty dissolves. In many films, they serve as gateways, points of no return that challenge characters to confront the unknown. These stories exaggerate, but they also echo a deeper truth. Black holes sit at the edge of understanding. One notable exception stands out. In the film Interstellar, scientists and filmmakers worked closely together to create a visual representation of a rotating black hole based on real equations. The result was not a chaotic void, but a smooth, luminous structure wrapped in a glowing disk of light bent into a delicate halo. For many viewers, it was surprising how calm and beautiful a black hole could look. When astronomers released the first actual image of a black hole in 2019, the reaction was similar. The image was soft, blurred, and strangely peaceful. There were no sharp edges, no dramatic contrast, just a warm ring of light fading into darkness. It looked less like a monster and more like a memory. Across cultures, black holes are sometimes imagined not as destroyers, but as thresholds. In myths and speculative fiction, they become doors between worlds, places of transformation rather than annihilation. This instinct reflects something ancient, a tendency to see darkness not as absence, but as transition. What often frightens people most about black holes is not what they do, but what they hide. They resist direct observation. They do not reveal interiors or intentions. And yet, as science slowly peels back their behavior, black holes become less threatening and more contemplative. They remind us that not everything needs to be visible to be real, that influence does not require noise, and that the unknown can be approached gently, without fear. As you listen, notice how your own image of a black hole may have changed, from a devourer to a presence, from a threat to a question. There is no need to settle on a single picture. Like all good stories, black holes allow many interpretations. Let those images fade softly now, leaving only the sense of something vast, patient, and quietly fascinating. To observe a black hole is to accept a certain kind of patience. There is no direct view, no clear outline to frame in a lens. Black holes announce themselves only through their influence, through the way nearby space behaves differently than expected. Astronomers learn to look not at the object itself, but at the subtle changes it creates around it. No telescope, no matter how powerful, can see a black hole directly. Instead, scientists watch the motion of stars, the glow of hot gas, and the bending of light. These indirect signs are quiet but reliable. Like footprints in snow, they reveal a presence without ever showing its face. One of the most ambitious efforts to study black holes came together in the form of the Event Horizon Telescope. Rather than a single instrument, it is a network of observatories scattered across the Earth, all synchronized to act as one. By combining data from distant locations, astronomers effectively created a telescope the size of the planet itself. This approach required extraordinary precision. Each observatory recorded vast amounts of data, carefully time-stamped using atomic clocks. The information was later brought together and processed over many months. The process was slow, deliberate, and meticulous, an approach well suited to the subject it sought to reveal. The result was the first image of a black hole's shadow, captured not by sight alone, but by patience and cooperation. The image did not show the black hole itself, but the silhouette it casts against the glowing gas behind it, a darkness outlined by light, shaped by gravity. Radio waves play a special role in this kind of observation. Unlike visible light, radio waves can pass through dust clouds that would otherwise block our view. They allow astronomers to listen where they cannot see, tuning into signals that carry information across immense distances without hurry. In many ways, studying black holes is an exercise in restraint. Scientists wait years for subtle changes in star orbits. They monitor faint fluctuations in radiation. They search for patterns that emerge only when enough time has passed. Nothing about black hole observation is rushed. This slowness mirrors the nature of the objects themselves. Black holes evolve over millions or billions of years. They respond to changes gradually. To understand them, we must adopt a similar rhythm. As you listen, imagine an observatory at night. The instruments are still. The sky turns slowly overhead. Data arrives not in bursts, but in steady streams. Somewhere far away, space-time curves, and that curvature leaves a faint imprint here. Understanding darkness does not require force. It requires attention. And sometimes the most meaningful discoveries come not from looking harder, but from waiting longer. Not all discoveries arrive with excitement or urgency. Some emerge slowly, almost reluctantly, after years of quiet observation. Black holes, especially, tend to reveal new details only when watched for a long time. Recent findings have not overturned what we know, but they have softened the picture, adding nuance where certainty once felt firm. For many years, black holes seemed to fall into two clear categories. There were stellar black holes, formed from collapsed stars, and supermassive black holes, anchoring galaxies. Between them lay a gap, a missing middle. Recently, evidence has begun to fill that space. Astronomers have identified black holes with masses between hundreds and thousands of suns. These intermediate mass black holes appear to be neither rare nor dominant, but quietly present, bridging an important scale in cosmic evolution. Some of these mid-sized black holes were discovered through gravitational waves, detected when they merged with others. Their signatures were subtle, requiring careful analysis to distinguish from noise. Others were inferred from the motion of stars in dense clusters. None announced themselves loudly. They simply left patterns that, once noticed, could not be unseen. Another gentle surprise has come from observations of light near black holes. In certain systems, astronomers have detected faint glows at the edges of accretion disks, regions where physics becomes delicate and complex. These bright rings are not sudden flashes, but steady emissions shaped by extreme gravity and rapid motion. They form slowly, persist quietly, and fade without drama. There are also black holes whose behavior seems almost restrained. Some feed at extraordinarily low rates, drawing in only thin streams of gas over vast periods of time. These black holes appear content to exist without growing, barely disturbing their surroundings. Their presence is easy to overlook, and many likely remain undetected simply because they are so quiet. Spin has added another layer of subtlety. Observations suggest that some black holes rotate at angles misaligned with the disks and stars around them. This hints at chaotic pasts, mergers, disruptions, and shifts long ago. And yet, in the present, these systems appear stable, as if old turbulence has settled into calm. What stands out in all of this is how unthreatening black holes become the longer we watch them. With time, patterns replace mystery. Behavior replaces fear. They transform from imagined dangers into understandable, if still profound, features of the universe. As you listen, imagine a black hole not as an event, but as a long observation. Something that reveals itself only to those willing to stay still and pay attention. No rush, no spectacle, just gradual clarity. Discovery, like gravity, often works best when allowed to unfold slowly. Black holes are often described as threats to life, as if their mere existence places the universe in danger. But when viewed calmly, their role appears far more balanced. They are not wandering predators. They are part of the structure that allows galaxies, stars, and perhaps even life itself to form in the first place. In the early universe, matter needed guidance. Gas clouds drifted through space, cooling and gathering slowly. In many galaxies, the gravity of a central black hole helped organize this material, drawing gas inward while also regulating how quickly it collapsed. In doing so, Black holes may have encouraged the birth of stars rather than prevented it. When a black hole becomes active, its influence can reach far beyond its immediate surroundings. Jets and radiation can compress nearby gas clouds, triggering new waves of star formation. At the same time, this energy can prevent too much material from collapsing at once, keeping a galaxy from burning through its fuel too quickly. This balance allows galaxies to evolve gradually instead of all at once. There is no evidence that black holes actively seek out life or destroy it. They affect their environments only through gravity and energy release, both of which follow predictable rules. Life, where it emerges, does so in regions far from black holes, where conditions are stable and calm. The presence of a black hole does not imply danger for distant worlds. In fact, a galaxy without a central black hole might be less stable over long timescales. The slow gravitational influence helps maintain order, guiding star orbits and shaping galactic structure. Calm systems tend to endure, and endurance is often a quiet requirement for life to arise. A simple thought experiment makes this clearer. If our sun were replaced by a black hole of equal mass, Earth would continue orbiting exactly as it does now. The gravitational pull would be unchanged. Only the warmth and light would vanish. Gravity alone does not create destruction. Context matters. Black holes remind us that influence does not equal harm. Something can be powerful without being hostile. Something can shape its surroundings without overwhelming them. As you rest with this idea, imagine a galaxy slowly turning, stars forming in gentle waves, guided by invisible centers of gravity. Life, if it appears, does so in pockets of calm, protected not by absence of force, but by balance. The universe is not arranged against life. It is arranged through long negotiations between energy, gravity, and time. Black holes are part of that negotiation, quiet participants in a process that favors patience over chaos. Let this understanding settle. There is room for stability, even near the deepest darkness. Imagine approaching a black hole without urgency, without fear, not falling, not fleeing, simply drifting closer as time stretches and the universe becomes quieter. This is not a journey meant to alarm, but one meant to explore perception, how reality itself softens under extreme gravity. From far away, nothing seems unusual. Stars shine as they always have. Space feels familiar, but as you approach, clocks begin to disagree. Your time remains steady, each second passing normally, yet the universe behind you starts to accelerate. Distant stars brighten and fade rapidly, as if the cosmos itself is skipping forward. For an outside observer, your motion appears to slow. You seem to hover, frozen near the edge of the black hole. Signals you send grow weaker and redder, stretching into longer wavelengths until they fade from view. From your perspective, however, there is no sudden boundary, no moment of impact. Crossing the event horizon would feel unremarkable. There is no wall, no shock, no sudden change in sensation. The laws of physics locally still behave as expected, at least for a while. The strangeness lies not in what you feel, but in what you can no longer see. Once inside, all possible paths lead inward. Forward in time becomes indistinguishable from falling deeper. The future points toward the center. This is not panic-inducing, but absolute, a quiet certainty rather than a dramatic collapse. In very large black holes, tidal forces at the horizon are gentle. You would not be torn apart immediately. Instead, the stretching would occur slowly, gradually lengthening your body along the direction of gravity. Sensations, if they could be perceived, would change over time rather than all at once. Light from the outside universe continues to reach you, but compressed into a shrinking region behind. The sky narrows. The past of the universe pours in, fast-forwarded, while your own present remains calm and continuous. Eventually, deeper inside, physics as we know it loses clarity. Our theories fade. Language becomes uncertain. What happens next is no longer something we can describe with confidence. The story ends not with terror, but with silence, a boundary beyond which explanation rests. This thought experiment is not meant to frighten. It is meant to slow the mind, to show how perspective shapes experience. The same event can appear frozen, accelerated, or peaceful depending on where you stand. As you rest, imagine this journey not as falling, but as drifting through layers of time. A soft descent into a place where direction and duration blur together. Even here, calm is possible, not because danger disappears, but because understanding replaces fear. Much of what we think we know about black holes comes from images, metaphors, and simplified explanations. Over time, these ideas harden into misconceptions. This section is an invitation to let some of those ideas gently fall away, replaced by a calmer, clearer understanding. A common image is that of a black hole as a cosmic vacuum cleaner, endlessly pulling everything toward it. In reality, a black hole's gravity behaves like any other object of the same mass. From a safe distance, its influence is no stronger than that of a star. Nothing is dragged in unless it strays too close. Another misconception is that black holes are constantly growing. Many of them are nearly dormant, barely feeding at all. They can remain unchanged for millions of years, quietly coexisting with their surroundings. Growth is the exception, not the rule. There is also the idea that black holes are perfectly black. Yet some of the brightest objects in the universe exist because of black holes. The glow comes not from the black hole itself, but from the material spiraling around it, heated by friction and motion. Darkness here is framed by light. Simplified diagrams often show black holes as deep funnels in space, with objects falling straight down. This image can be helpful, but it hides an important truth. Space and time are both curved, and motion through one affects motion through the other. What looks like falling is also moving forward in time. People sometimes imagine that crossing the event horizon is instantly fatal. For large black holes, this is not the case. The horizon is not a physical surface. It is a boundary defined by speed and direction. You cross it the way you cross a line on a map, without noticing the exact moment. Even the idea of the singularity, an infinitely dense point, may be an oversimplification. Our equations predict it, but they also signal where those equations stop working. The singularity may be less a physical object and more a sign that deeper physics awaits discovery. Real black holes are not isolated objects floating alone in space. They interact with their environments, shaped by nearby stars, gas, and even other black holes. Each one has a history written into its motion and spin. Understanding black holes is not about replacing wonder with certainty. It is about exchanging fear for familiarity. The more accurately we see them, the less monstrous they become. As you listen, allow these ideas to soften. Let go of sharp edges and dramatic images. What remains is still mysterious, but it is a mystery that invites curiosity rather than alarm. Clarity, like gravity, does not rush. It settles slowly, reshaping understanding over time. Long before anything reaches a black hole's edge, another force quietly takes over. It does not roar or strike suddenly. It stretches gently at first, then with growing insistence. This is tidal force, the difference in gravity between one part of an object and another. Near a black hole, gravity does not pull evenly. The part of you closer to the center feels a stronger attraction than the part farther away. This difference creates a slow, steady stretching. Not a snap, not a tear, more like being drawn into a longer shape over time. This effect has a calm but unavoidable name: spaghettification. It sounds playful, but the process itself is purely physical. Arms, legs, atoms, even light are guided along curved paths, aligned with the direction of gravity. Everything becomes elongated, following the geometry of spacetime. In small black holes, this stretching becomes intense very quickly. Long before reaching the event horizon, tidal forces would overwhelm any structure. In large black holes, however, the gradient is gentler. The stretching begins slowly, giving time, at least conceptually, to observe the process unfolding. What's important is that this force is not unique to black holes. The moon creates tides on Earth using the same principle, just on a much softer scale. Black holes simply amplify what already exists, turning a familiar effect into an extreme one. From far away, tidal forces sculpt galaxies. They pull stars into streams, stretch clusters, and rearrange matter over billions of years. Even here, the process is unhurried. Nothing is rushed. Gravity prefers patience. As you rest with this idea, imagine being gently lengthened, not harmed, simply reshaped by a gradient too subtle to notice at first. The danger is not sudden. It is progressive, predictable, and deeply tied to the structure of space itself. The universe rarely acts abruptly. Even its most powerful forces usually arrive slowly. Understanding tidal forces is another reminder that black holes are not violent by default. They are precise. They follow rules. And those rules unfold at a pace that invites observation rather than panic. Black holes often appear in discussions about the future of space travel, not as destinations, but as possibilities. Sources of energy, gateways, shortcuts. These ideas belong more to speculation than engineering, yet they reveal how deeply black holes capture human imagination. One proposal suggests using the rotation of a black hole to extract energy. This is not fantasy. The Penrose process and similar mechanisms describe how energy could, in theory, be drawn from a spinning black hole's motion. The idea is elegant, but the practical challenges are immense. Another recurring concept is the wormhole, a tunnel through space-time that could connect distant regions of the universe. Some solutions to Einstein's equations allow such structures, but keeping them open would require forms of matter we have never observed. Without that support, a wormhole would collapse into a black hole almost instantly. Black holes also shape future navigation indirectly. Their gravitational effects act as reference points, anchoring galaxies and clusters. Understanding them improves our ability to model cosmic motion, predict long-term stability, and map the large-scale structure of the universe. There is no realistic plan to travel near a black hole. The risks outweigh any benefit, yet studying them helps refine the physics needed for any deep space journey. They are laboratories where theory is tested under extreme conditions. The future does not require black holes to be useful. It requires them to be understood. Knowledge, not proximity, is what turns danger into insight. As you listen, imagine a distant future where black holes remain untouched, observed from afar, respected rather than approached. They continue their slow rotations, their quiet influence unchanged by human ambition. Some doors are not meant to be opened. They are meant to be studied from a distance, teaching us about the limits of motion, energy, and time. The most practical lesson black holes offer may be restraint. Black holes are not the only ending stars can reach. Many stellar lives conclude more gently, settling into states that are dense, stable, and quietly enduring. These alternatives help place black holes in context as one outcome among several, not an inevitable fate. White dwarfs are the remnants of stars like our Sun. After shedding their outer layers, they leave behind a hot, compact core that slowly cools over trillions of years. Nothing dramatic happens. The star simply fades, holding itself up through quantum pressure. Neutron stars are denser still, formed from massive stars that collapse but do not quite become black holes. They compress matter to extraordinary levels. A teaspoon of neutron star material would outweigh a mountain. Yet even here, structure remains. Some neutron stars become pulsars, spinning and emitting beams of radiation with clock-like precision. They are among the most reliable objects in the universe, marking time more accurately than many human-made systems. These stellar remnants are not steps toward black holes. They are stable endpoints in their own right. Only stars beyond a certain mass cross the threshold into complete collapse. Understanding these alternatives helps soften the narrative. Black holes are not the default conclusion. They are a specific solution to a specific set of conditions. As you listen, imagine the many quiet endings scattered across the galaxy. White dwarfs cooling, neutron stars spinning, black holes resting. Each one is a form of cosmic sleep, different in depth, different in character. The universe allows multiple forms of stillness. Seeing black holes alongside their gentler cousins makes them feel less extreme. They are part of a spectrum, not an anomaly. We have reached the end of the 100 facts, but not the end of the mystery. Black holes remain among the most complete predictions ever confirmed, and yet among the least fully understood. They sit at the intersection of certainty and ignorance. They confirm general relativity with stunning accuracy. At the same time, they expose where that theory breaks down. Inside them, our equations fall silent. Something deeper waits, unnamed. We know how black holes form, how they grow, how they merge, and how they fade. We do not know what ultimately happens to information or how gravity behaves at the smallest scales. These unanswered questions are not failures. They are invitations. Black holes teach us patience. They evolve slowly. They reveal themselves indirectly. They reward long observation rather than quick conclusions. For a series meant to ease the mind, this may be the most important lesson. The universe is not in a hurry. Its most powerful objects act over immense timescales, guided by simple rules applied consistently. As you rest, Imagine the universe continuing long after all sound fades. Black holes remain for a while, then even they dissolve into faint radiation. Time stretches, space cools, nothing dramatic happens, and yet meaning remains not in events, but in understanding. The facts end here. The quiet does not.